Okay, hi again. This is the second part of the video, and on this one we're going to continue with the demo example. Let's go on. So the first thing to do is to download go to the website, the GitHub page, targeting group, crystal plasticity, and download this code. I'm going to do that just to show you, and we extract it all. Of course, in a proper place, but for now it's fine to have it somewhere. Okay. And here we have the latest version of the code. This is the latest version, and if we double click on that, and you see there's this UEL, so that contains all the functionality required for cohesive zone modeling. So this is what we're going to use. So I'm going to create a new folder here, test, just to work on, and just copy this directory, and I'll go ahead and open up ABAQUS. Make sure you've got the Intel function and the compiler, the Visual Studio coupled. So I'm going to create the file from scratch, but you could use Dream3D or Napper and run this thing, run the cohesive functionality to add the cohesive elements at the grain boundary interfaces. So that's the whole purpose of this work. It could be also a phase boundary, could be any other kind of boundary that you want to put these cohesive elements. Just have to define the correct way of naming the sections and material numbers. I'll show you in a moment. So just set the working directory here, and I will create the part. Okay, I would use like a 0, 0 coordinates and go to 2 to 1. Okay, and should do it. That should be 1. Okay, so this is our break. I'm gonna cut the partition into 2. So I'm gonna use this partition 2. Let's try the 3 points. Okay, this one, and that one. And if you say create partition, this should be able to create the partition we wanted. Okay, that's great. Next, we're gonna create the materials. Let's create the materials. Well, for the code, we have to create the solution-dependent state variables, which is the UMAT solution-dependent state variables, which should have the same number as the output. I think I described this earlier in the earlier videos. We also have to create the user material to call that. It will call the UMAT for the solid material properties. Let's put these other angles 0, 0, 0, and this is grain number 1. This will use material number 2, and it will use user materials.f. So I think that should be it. Then if we copy this, create another material, then we edit that, just change the other angle to 45. That should do it. Okay. Now let's create the sections. Sections will be, section 1 will be homogeneous, will be material 1, let's be consistent, and another section for material number 2. So that's straightforward ABAQUS stuff. What we have to do is assign the sections in this part. So what I'm going to do is just assign. We have to create a set for each section, and that's a very important variable name. I will explain you what. So I'm not going to change this, I'll just call it set1 for now, and select the region to be this one, and then set done. And I'll select the section 1 to be consistent. It will be the material 1, okay? And the section 2, select the regions, that one, okay? I'm going to select this as done, and it's going to be section 2 as material number 2, and that's it. Okay, and next we go create the mesh. Let's go create full integration C3D 8 elements. Okay, and let's put a mesh of just one element, approximate size of that. And let's mesh it done. Okay, and I think that should be it. But I'll tell you a couple of things later. So we could add also the steps or bounded conditions, but the code in the generator I actually overwrite these variables. So let's stick with creating the input file. Let's go ahead to create the input file. Let's set OK, and then write this as our input file. Okay, write input. Oh, we forgot the assembly. Sorry, we forgot the assembly. Just have to create this assembly, the instance create. Okay, that should do it. Okay, now let's create the input file. Maybe I should also add the steps. Should add a step just to make sure we add this step. Nonlinear geometry, the time period 10 seconds. Let's add that up. The implementation, no one, and let's keep the maximum to 0.01, and let's make this 1000, and let's make this 0.5. Okay, and let's write this as the input. Okay, now here we created the input file here. Okay, so this only contains the solid elements properties. Now we have to take this to this add cohesive function, which is this add cohesive elements folder. So there's a MATLAB way, and there will be a Python way to put it as well. So I'm gonna put this file here. Okay, and let's open this up in MATLAB. So I go to MATLAB, just go to that directory. Okay, and here open up the input file. Okay, so here there are some inputs, not too many, but a few inputs. So there is this file name we have to enter, which is job one, right? It's our file name. So there is grain set name. We didn't set it as, it depends on what mesh generator you use. Like Demper or Dream3D uses different text for these grain sets. But in this case, we have set one, right? So we have our element sets are set one. So we have to tell that as our set name. So it's just going to be until the number. So that will be one, but we don't write the number, just set dash. And the material number, the material identifier is at the end. It's material one. So we have to put this as a text here. So I'm going to write it case sensitive. And a new file name will be that. We will use material number 2. Number of state defining variables are 12. We have the Gauss quadrature. Okay, here are the UEL properties. We want to use mixed mode. These are the stiffness values. Let's use the values that we are given. We are given as 50 megapascals, the fracture strengths, and this is the fracture toughness, 0.5, and VK exponent and thickness, but it's not relevant. Okay, so let's try running this, see what it does. Okay, that's it. It's very simple because there's just one element. So it created this file. Let's see what it did. So it added a few more nodes. If you realize there's 4 more nodes additionally added here, and it added this user element here with the properties, and as for the given element type, which is C3D8, and it also modified the connectivity of the solid elements because of the additional nodes introduced. So okay, let's call this then step 5, the simulation step, or well, let's go to the, yes, let's call it step 5. step, and just put this, take this cohesive file, put it in there, and let's go to ABAQUS now. Let's, I don't know, save this as test. Okay, I'm gonna close this, and we put it at cohesive, this one. Okay, we go to this working directory. Now, the using user element is slightly different than UMAT. So we cannot put the input file directly. So we cannot use this import functionality. Instead, we should call from the jobs. Okay, so you just go to jobs, create input file, select the input file we have. Unfortunately, we won't be able to visualize anything. Setting the scratch directory and set the UMAT, point to the UMAT file, which is going to be the Oxford UMAT file. Okay, and that's it. And then just run it. Well, before submitting, we could have changed some other things, but let's have a look. Until it compiles, we still have time. So, okay. Right. Okay. So these are the maximum and minimum steps, the time steps. We have to change them to maybe 0.01, and maybe change this to 0.5. Tell you in a moment. I think this is the maximum time step, but let's see. This is the starting one. Not sure if it's the maximum. But yeah, this is the end time. I think this is the end time. This is the minimum time step, and this is the maximum time step. Yes. Let's allow it to be a small time step because it can cause some problems when we have very large time steps for this case. Let's see. Okay, it's still doing something. Okay, let's look at the, so this is like the applied 10% strain. The size is, well, actually, yes, we can call it like 10% for the grain. And these are the material properties for grains. They're going to use user material. So it will point to the Oxford UMAT, and the rest should be okay. It's going to use the mixed mode property. These are the penalty stiffness values. These 50 megapascals are here. 2.5 fracture toughness, BKX1 and 2, and thickness as 1, which is not relevant. It's just this additional element that is cohesive properties. 1 and 2 are the solid elements. So the reason when we use UEL, unfortunately, we won't be able to visualize the properties of the UEL in ABAQUS. To be able to visualize it, there are some tricks to do it. But in that case, we have to make the cohesive element with some finite thickness. It's doable, but we have to use finite thickness of the cohesive element. So if you look at the results file, it's still not generated. I'll show you the results of once it's generated. Then we should be able to visualize at least some of the results. Yeah, and this can work with Nepper Dream 3D outputs, and they can. It's basically designed to looking at these text from these given identifiers. Yeah, but we just did it for a bicrystal simple case that we created all ourselves, but it works with Dream 3D and Nepper as well. I did use it for different purposes. Yeah. Okay, started running. Start doing something. Let's see if it's gonna work. All right, let's look at the results. So you see there's these two elements, and there's cohesive element in between. It already made some steps here. So there's this cohesive element in between here. Um, did now did go to very small time steps. I did the wrong thing. Well, let's see what it did. So we can look at the force displacement response. This. So for example, we can set from this boundary, choose these nodes and save them. And then we can have a look at some of these reaction forces to see how this cohesive element reacts. So, all right, so if you look at these, it's probably did a very small time step, but you can see that it could reach it up to 50, which is 51 times 1, which is 50, which is our dimension initiation strength, and it went down to this value. If you look at the area of this curve, it is 50 times 0.01 divided by 2 is 2.5, which is consistent. So if you look at the strain rates, there is some flip going on in one of the grains. Maybe this grain is softer because it's cube. This is Gauss grain. It's not really deforming. Um, yeah, so this grain is mostly rigid, but the other one is deforming. So there's slip going on in this one, but not slip going on in this one. So it just breaks when it reaches the magnitude. It behaves like an elastic material. Okay, I think I'll finish with this, and please ask your questions by raising issues to the GitHub page, and don't forget to like and subscribe the video. Thank you.